Hello all, welcome to this tutorials in which we will be seeing an example of the Neiman-Pearson classifier that we have discussed in our earlier tutorials. Now, just to give you a small recap on the last tutorials, now we constructed a classifier uh, now which is bounding the type 1 error by alpha, and then whatever hypothesis function that satisfies this, the one that is giving us the least type 2 error is what we are considering. And then now whenever we have classifier of this condition, okay, wherein which we take the decision based on the ratio of class conditionals, that is a Neiman-Pearson classifier. We proved it using the conditions. That is where we have stopped in our earlier discussion. In today's discussion, what we shall be looking at is we'll be looking at an example of Neiman-Pearson classifier, and then we will be looking at a very interesting uh, idea called as ROC. Okay. Now, without any further delay, let's proceed. Now we will be looking at the example of Neiman-Pearson classifier. Now, what are the X belongs to R? Your samples belongs to R. Okay, and then the class conditionals are the class conditional densities are normal with equal variance, and then without loss of generality, we are assuming that mu0 is less than mu1. Okay. So now what is that we want to do? No, we want to come up with a threshold. Okay, so now one can show that the NP classifier is if given X is greater than the tau, then I'll say that it's class 1. Now, how do you determine this tau? Now, where tau is determined that bound on the type 1 error. Okay, so where tau is determined on type 1 error bound. Now, what do you mean by that? Now, it means that the integral from tau to infinite x dx to alpha. Okay. So now we have seen this diagrammatically also. If you look at this, now if you consider this as tau, from tau to infinity, now what is the area under the class conditional of the zeroth class? Okay. Now that's what. Now this blue area is what you're calculating, and that is what is the alpha that you have bounding. Okay, fine. So now we know that this, now Bayes classifier minimizes risk, which is a kind of the weighted error. Okay, this we have seen earlier also, which is a kind of weighted error. Okay, so now, and we know that the NP classifier is a way of deciding how to trade one type of error with another. Okay, NP classifier is another way of deciding how to trade one type of error with another. Okay, we have in detail look at it. Okay, so now for a two class problem, now what it boils down to for a class problem, for a two class problem, one can always trade false positive rate against false negative rates. Okay, and this we have already seen. Now we know what is false positive. Did we look at it? Sometimes yes, yes, false positive and false negative. Yeah, just I wanted to know that whether I have introduced those nomenclature. Okay, now, now what do we want? Now we always want a threshold which can be tuned to take care of this trade-off. Okay, now we want to tune it. That means that we have to decide on it. Okay, so now we would always have a threshold which can be tuned to affect this trade-off. So now you have a lot of options. So now what is the best that you want? Now depending on a threshold, I should be able to look at it. Okay, now I should be able to take care of it. And this can be done using now what is known as ROC, receiver operating characteristic curve. Okay, now is a good way of looking at it. Is a convenient way of looking at this trade-off. That's what I mean by that. Okay, so now let's consider that one-dimensional feature. Let's put all of them together. Now, consider one x belongs to R and a two-class problem. Now then my h of x is equal to 0 if x less than this tau. Now I will consider equal priors, okay, and then class conditionals with equivariance and then 0-1 loss. Okay, on this now consider equal priors equal priors, Gaussian class conditional normal, class conditional densities with equal variance and 0 1 loss. Okay. Now then from our earlier discussion, the probability of error, which is we have obtained, it will be 0.5 from minus infinity to tau, x given y is equal to 1 of x dx plus c now, okay, plus 0.5 into tau to infinity x given y is equal to 0 of x dx. Now again, I just want to reiterate this. Now this orange that you are seeing is class 1. Now you can see that what is risk? This area and this area. Okay, that's what you are considering. Fine. So now this you can easily compute. Now you can substitute. These are Gaussian. Now you can substitute, and then we can immediately see that now this will turns out to be 0.5 into phi of tau minus mu1 divided by sigma plus 1 minus phi of tau minus mu0 sigma. This will be my error. Okay. Now, depending on my value of tau, I can compute the error. Okay. Fine. So now, let's make a note of this. As we vary tau, we trade one kind of error with another. Now that means that as you move that tau, okay, there will be a trade-off between one kind of another error to another. Okay. So now whenever you consider a two-class problem in a two-class classification, there will be four possible outcomes. Okay. Now, two we have already seen. There will be four possible outcomes. Now, what are those four possible outcomes? Let's try to write them. So now let's define EI, now which denote the probability of wrongly assigning class I. Okay, you're wrongly assigning class I. So now there are two cases. Okay, now I'm assuming that C1 is the positive class, C0 is a negative class. So now then we decide C1 if x is greater than tau. Now then this gives rise to E0, that is what is the probability that I'm wrongly putting it to class I. Now that means that when do I wrongly put it into class? X is less than tau. That is when I wrongly put it into class 0 when X actually belongs to C1. Now what is the probability of this is what I am asking. Now this is falsely put as negative, right? Now this is false negative rate. Similarly, I can have E1 where in which X is greater than tau. Now that is when you assign it to 1, but actually X belongs to the negative class. What is the probability of it? This is known as the false positive rate. Okay. So now we can have the complements of these. Okay. Now I can have 1 minus E naught. And then it will be the probability that X greater than tau and X belongs to C1. Now this is true positive rate. And similarly, I can have 1 minus E1, now which is probability that X is less than or equal to tau, given X belongs to C naught. This is true negative rate. Okay. Now I assume that these terms are comfortable. Okay. Now whenever we have these things, we come up with the two more quantities of interest that in most of the binary classification problems, now you will be seeing them repeatedly. We have two quantities of interest is of interest. Now one is what is known as the precision, which is true positive divided by true positive plus false positive. And then we have recall, that is true positive divided by true positive plus false negative. Okay. Now I assume that you will be able to write these in terms of these probabilities. Okay. So now these are two quantities that we always look into whenever we are looking into the problem of binary classification. And then now sometimes we take the harmonic mean of this and then call it as an F1 score. Okay, that is an outcome of these two quantities, so we will not look into it. Now you will be capable enough of looking at this. Okay, so now coming back to the way of choosing the threshold, which was our actual need. Okay, so now it is quite clear that as I change my tau, now there will be a change in E1 and 1 minus E naught. Okay, so now for a fixed class conditional, densities, if we vary tau, the point E1 and 1 minus E naught moves on a smooth curve in R2. Correct? So now, for a fixed tau, we can always estimate E0 and E1 from the training data. So now, hence, if you vary this tau, okay, now we can find this ROC and decide now which is the best point that we actually need. Okay, what is the point that gives us the good trade-off that we need? Okay, so now this is evident that hence varying the tau, we can find ROC and decide which may be the best operating point. And that means what is the best trade-off that we need for our given case. Okay. Now, as you can see, this can be done for any threshold-based classifier. Okay. Now, this can be done for any threshold-based classifier irrespective of class conditionals. Now that's what we shall be looking at in our demo now, which I was showing. Let me run this. So now this is for the previous run. Okay. Now you can, let's first try to understand this. Now this is the blue one is the class 0 and this orange is class 1. Now you can see that now this is class 1 which is being what do you call classified as class 0, and this is class 0 classified as class 1. Now false positive and false negative, now you can easily see. Okay, so now I have I have calculated the base risk. Now that is 0.158655, and this is my ROC curve. Okay, now as I vary my threshold, now you can see that the true positive rate and the false positive rate. Now that is E0 and 1, E1 and 1 minus E0. Okay, this is 1 minus E0, this is E1. When I vary this, now your risk varies. Now whichever is the best risk that you want, you can choose it. Okay, so now I have put a small tool to look at it. Okay, now you can see that I have varied this. Now you see this, what has happened. Now your classifier has moved. Okay, and then this is the overall region that is you have considered as a false positive, and then I can actually move this. Then we can come with this orange dot now, which is there, is actually the base error, wherein which you are getting that whatever is the value 0.158. Okay, and now you can see this. Okay, as you can see here, as I modify this, you see that which point you want. Okay, now how should be your trade-off? Now depending on it, you can decide what do you want. Okay, you can decide on it depending on the threshold. You decide when to put, and you can know the trade-off that is there between the two kinds of errors. Okay. best thing that you get is at what this is. Okay. So this is what I have been trying to explain you, that as you vary the tau, your trade-off between one type of error and other type of error actually varies, which you can programmatically see now in this particular given animation. Mm, okay. This is where I have considered one-dimensional feature and then the class conditionals with equivariance, and then I have tried to come up with this particular animation, which is there. Okay. Now I assume that all the dots that we have been discussing is able to what do you call obtain it at a nice place. Okay. So now let's go back. Couple of small minute details that we need to have. Okay. So now when the class conditionals, class conditional densities are normal with equal variance, E1 is from tau to tau to infinity. This is not minus infinity, it is tau to infinity. Probability that x given is equal to 0 of x dx equal to 1 minus psi mu naught divided by sigma, and E naught is minus infinite to tau, that x given y is equal to 1 of x dx. Okay. See, the point is, whenever you write equations, no, now at least at an intuitive level, for a simple one-dimensional features, we should be able to visualize what is happening. Okay, that is the reason why we have all these diagrams now that are there. We should be able to visualize what is the integral from where to where is happening. Now once you have that, in at least the intuition should be quite comfortably clear. Okay, that's needed. Okay, now from the error integral, now let's calculate the tau. Okay. So now from the error integrals, from these integrals, we get tau minus mu naught sigma is the inverse of 1 minus E1. Let's say it as A. Okay, and then tau minus inverse 1 minus of naught. Let's call it B. Okay, so then comes the interesting thing. Then if I take the modulus of A minus B, now this is mu1 minus mu naught divided by sigma, and you see this is called as discriminator, which is not dependent on tau. Okay, this is called the discriminator, which is not dependent on tau. Okay, so now knowing E1 and 1 minus E naught, we can uh, get this D, and hence we can get the Bayes error. Okay, so now for any given tau, we can also get actual error probability, and we can tweak this tau to get the Bayes error. That's what we actually did. Okay, we can get this, we can tweak this tau to match to the Bayes error. Okay, and whenever we are plotting this ROC curve, no, there is one more thing that we do. So we always join the 0, 0 and 1, 1. Now this is what is known as a random classifier. This is y is equal to x line, which is there. Now the area under this ROC curve is what is known as AUC, area under the curve. Okay, and it's a very good indicator regarding the quality of the classifier. Okay, so now the curve that you get, the ROC curve, should not be below the y is equal to x line. Okay, now it has to be always above that. Now what does it indicate? Now it's just it's a random classifier. That means that you take a coin, and then you just depending on the toss of the coin, you decide what is the class. Okay, now that's not even learning in any case. Okay, so now in that situation, no, the classifier that we come up, whatever might be the classifier, has to be better than that random classifier, which is the y is equal to the x line that we get. Okay, so now that's the one more important thing about this ROC. Okay, so now with this we conclude this tutorial. I hope that you understood the importance of this threshold and how do you manipulate this threshold that gives rise to a very nice, interesting idea called as receiver operating characteristics ROC curve. And then the outcome of this, the area under this ROC, which is known as AUC, area under the curve, which is a good indicator of the classifier. And then it also gave rise to a couple of interesting quantities like precision and recall, which are quite important whenever we are dealing with the classification tasks. Okay. Now with this, we conclude today's tutorials. Now I hope it was helpful. Thank you. Let's meet in the next tutorials. Bye-bye.